Hi, Chem 151 students, and welcome back to the second lecture this week, week 11. What we're going to be dealing with now is some of the concepts behind analyzing titration curves and analyzing titrations problems. So before we jump into some heavy-duty calculation, we want to make sure that we understand what it is that we're calculating. So by now, you've done quite a lot of calculations about equilibria. You know the mechanics of it, you know how to use the simplifying assumption, how to write the equilibrium constant expression to plug in the appropriate concentration stated in terms of x, then to solve for x and figure out equilibrium concentration values or the pH. But what's hard about these problems is not going through that process, really. You guys are becoming increasingly familiar with that mathematical process. The hard part is knowing what equilibrium that you're actually considering and understanding what is actually going on in the question so that you can write the correct reaction and analyze the correct equilibrium. And so before we even start to do any numbers in this lecture, I'm going to focus on how it is that we're going to approach questions and what kind of answers we can expect to find when we solve the problem. That's also something you should always keep in mind is if you get an answer that is not consistent with what you understand about the question, what it probably means is that there was a math error somewhere. And if you understand the question thoroughly, you can catch that math error before you get the question wrong, and you can correct your work and get full credit. In more realistic scenarios, it means that you'll do the calculation or that you were intending to do correctly, or you will understand the problem that you need to understand. So first of all, let's talk about what a titration is. So you guys have been doing lots of titrations over the course of the semester. The semester is basically a whole bunch of titrations, but it's a procedure for determining the concentration of an unknown solution by reacting it with a very carefully measured volume of a standard known solution. And so you have a solution that is in the burette, which is a standard solution. You know the concentration. This is often also called the titrant. And then you have an Erlenmeyer flask containing a solution of unknown concentration, and you're trying to determine that concentration. Usually, the point at which a 1-to-1 mole ratio or a stoichiometric mole ratio, if it's not 1-to-1, is reached, there will be some type of indication like a color change that occurs. And usually, if you're doing an acid-base titration, you're going to add an acid-base indicator that will change color in the same pH range that is changing within your reaction in the flask. And so you guys saw some titrations you did previously in the lab. You use for all of your titrations, you use the acid-base indicator phenolphthalein, which changes color at pH approximately 9. And you probably found that that was pretty good for 2 of your titrations, but it didn't really work much at all, or maybe barely change color for the other 2 titrations. So the choice of indicator is very important. You want to choose an indicator that will change pH in a range that is consistent with the pH of where you have a stoichiometric ratio between the acid and the base that you're analyzing. So here's a setup for a pH titration. Same setup you guys had last week. So you had pH meter held up by a clamp. I don't know what, they're not holding theirs up with a clamp, but they don't have a stir bar in the bottom. And the burette here contains sodium hydroxide. The beaker here contains some HCl, and the pH is measured while NaOH is added. That's exactly what you guys did in the lab. And so this is a strong acid, strong base titration. So what you saw was we started off at low pH, pH 1, because it's 0.1 molar HCl. This is exactly what you guys did in the lab. And add NaOH, and the pH was pretty flat for a while, then suddenly jumped up. and increases. So the pH increases gradually before the equivalence point, and then this is the equivalence point. So the equivalence point means when you have the same number of moles of HCl here as you do NaOH. Since they were both 0.1 molar and we started with 40 milliliters of HCl, the equivalence point arrived when we had added the same volume, 40 milliliters of NaOH. And for a strong acid, strong base titration, the equivalence point is neutral, because once you have neutralized the acid here, all you have is sodium ions, chloride ions. These are neither acidic nor basic. They're both neutral. They don't create acidic or basic solutions, so the pH is 7. It's a neutral pH. Then the pH rises rapidly, and then eventually, once all the acid is used up, the solution becomes closer and closer to pH 13, which is the pH of this 0.1 molar sodium hydroxide. So the equivalence point is defined as the point at which the stoichiometric equivalent quantities of acid and base have been mixed. Usually that's 1-to-1 molar ratio. It can be different, but it's usually 1-to-1. So there's going to be 3 different types of titrations. We can have strong acid, strong base. For these titrations, there's no equilibrium. So the pH is going to be decided based on whatever there is an excess of. If there's excess H+, that will decide the concentration. If there's excess OH-, that will decide the pH rather. So whatever there is remaining, H+ or OH-, calculate the pH based on that. In a weak acid, strong base titration, we first assume that the strong base reacts completely. So that's what we did when we were doing those buffer problems where we added a strong base to the buffer. We assume complete reaction of the strong base. After that, then we will perform an equilibrium calculation and determine the pH based on the quantity of the weak acid and the conjugate base that are in the solution. The other type is strong acid, weak base titration. So here we assume that the strong acid reacts completely, and then equilibrium will be determined based on the amount of weak base and its conjugate acid that are in the solution. There's one other type of titration you did in the lab. It was weak acid, weak base. And that is not a titration that's very useful analytically, because we can't make that same assumption that the strong acid or strong base reacts 100%, because there is no strong acid, strong base in the titration. So when it comes to calculating pH values, there's going to be 3 types of titrations we do, because calculating the pH of a weak acid, weak base mixture is actually quite a complicated matter. And so that's not going to be something that's in this class. It's beyond the scope of this class. So just like we saw when we were dealing with the buffers, when we deal with the titration, there's always going to be 2 steps to the calculation. The first step is going to be a stoichiometry step, where we assume that the strong acid or strong base reacts till it's all gone. Or if the other component runs out first, then there will just be excess acid or base left in the solution. Now, what's different about the calculations we're going to do for titrations, what's different from the buffer problems we did before, was that we're going to have various stages of the titration at which we can calculate the pH. And our approach and our strategy for calculating the pH at different points in the titration is going to be different. If we are in the titration and it's before the equivalence point, as we're adding the strong acid or strong base, that's going to neutralize the weak component that it's titrating. And you're going to get a mixture of weak acid conjugate base in the solution. You'll have a buffer. In fact, they call this the buffer region before the equivalence point. So you'll do your step 1 stoichiometry and figure out the concentrations of acid and conjugate base in the solution. And then you can determine the pH using the Henderson-Hasselbalch equation, because you will have a buffer at this point. Or you could do it using an ice table, either of the two methods that I showed you last time. Of course, the Henderson-Hasselbalch equation is here. So before the equivalence point, you're going to have the weak acid or base and its conjugate in solution. So you're going to have a buffer, and you'll be able to calculate the pH of that using the Henderson-Hasselbalch. If you are at the equivalence point, at that point, all of your initial weak acid or weak base in the titration will have been completely consumed. So you will perform you will write an ice table and perform an equilibrium calculation based on the remaining conjugate acid or base that's left. So at the equivalence point, all of your initial weak acid or weak base is gone. All that's left is the conjugate. So you're going to perform an equilibrium calculation to determine the pH based on the remaining concentration of the conjugate acid or base of your original weak acid or weak base. You're going to use a standard ice table. You can't use the Henderson-Hasselbalch here because you're not going to have a mixture of weak acid and conjugate base. You're only going to have one of them. So the Henderson-Hasselbalch equation doesn't apply there. Finally, if you're past the equivalence point, then all of your weak acid, weak base that was left in the solution doesn't even matter anymore. Your pH is going to be dominated by your excess strong acid or strong base that you're adding. And so all you have to do is determine how much strong acid or strong base remains after it was neutralized by the other thing that you were titrating, and determine the pH based on that. So what I'm going to do now is I'm going to look at the shape of a variety of titration curves, explain to you how you can tell at what point of the titration you're in, and then talk about each of these points in the titration and what will be the relevant equation that you're going to write down to analyze the pH at that point in the titration, because that's the most important part. You can't do any of this calculation stuff if you're doing it for an equilibrium that's not there, or for some components that are not even in the solution. First thing you have to do is write the correct equilibrium equation, or first write the correct stoichiometry equation, then write the correct equilibrium equation. So we're going to focus on doing that first, and then we'll go through some very involved calculations. But it's really important that you can identify the real reactions that are important to this, to each point in the titration, before you even start plugging numbers, punching your calculator, and so on. So let's focus on strong acid, strong base titration to begin with. So here, we're doing a titration, 40 milliliters of 0.1 molar HCl being titrated with 0.1 molar NaOH, strong acid, strong base. At the beginning of the titration, all we've got in the flask is 0.1 molar HCl. So the pH is, so this is the concentration of hydronium. The pH is the negative log of 0.1 molar, which is just 1. So the pH is 1 to begin with. Then we begin to add sodium hydroxide. And so now what's going on is hydronium's reacting with hydroxide to make water. We assume 100% reaction. Now you may be asking, what about the sodium in the sodium hydroxide? That is a spectator. It's not reacting, so it's totally appropriate to remove it from the equation. Of course, we'd have over here on the right side, we'd have aqueous sodium chloride as another product. But we don't even have to write that, because the sodium ions and the chloride ions aren't doing anything. Aqueous sodium ions, aqueous chloride ions, they aren't doing anything. It's spectator, so that's why we didn't write it. Now, what about HCl, right? It wasn't H3O plus, it was HCl. H plus and Cl minus. Again, chloride ions here, spectators. They didn't do anything. And we can write H plus as H3O plus. These two things mean the same thing. So what's really going on is H plus from the HCl is reacting with OH minus from the sodium hydroxide. They're making water. Water is neutral. There's also sodium chloride, a neutral salt. Once we get to the equivalence point, pH will be 7. So here we still have excess hydronium. We have not added enough hydroxide to neutralize it, and so the pH is rising, but still slowly. Finally, we reach the equivalence point. Here, the H3O plus and the hydroxide have completely neutralized each other to make water. Water's pH 7, so the equivalence point for a strong acid, strong base titration occurs at pH 7. Then we begin to pass the equivalence point. At this point, we're just adding more hydroxide. All the hydronium is gone. So the pH is now determined by however much hydroxide we have remaining, since we're past the equivalence point. Now, that's a strong acid, strong base titration. Relatively straightforward. If we're before the equivalence point, we have excess hydronium. Calculate the pH based on how much hydronium is left. If we're at the equivalence point, pH is 7. If we're past the equivalence point, the pH is determined by the excess hydroxide. So get the POH, negative log of hydroxide, then find the POH, 14 minus the POH. Very straightforward. No equilibrium calculations to do. Okay? Just before the equivalence point, based on how much acid's left. At the equivalence point, pH 7. After the equivalence point, however much hydroxide is left over after it was neutralized by whatever hydronium was there. No equilibrium to deal with, because there's no weak acid or weak base. Now, for a weak acid, strong base titration, now we have a weak acid. Things get more complex. So a couple of things here. You guys did both of these titrations in lab. The first one you did was HCl and NaOH. What you probably noticed was that it started off lower because you had the strong acid at pH 1, and there was a larger period of rise before it leveled off. Here is your weak acid strong base titration. So your weak acid was acetic acid. Strong base was sodium hydroxide. So this was the second titration that you did. Okay. And you used phenolphthalein for both these titrations. And phenolphthalein was a fine indicator for this titration because it changed color during the region where the pH was rapidly rising. Now, it's fine for both of these. For the strong acid, strong base titration, perhaps a indicator that changes color around pH 7 might be slightly better. But as long as it changes color in the region where the pH is rapidly rising, it's a fine indicator for that reaction. Now notice methyl red here. This changes color in the region pH about 4 to 6. So this indicator would work okay for the strong acid, strong base titration, but it would not work at all for the weak acid, strong base titration. So note that when you choose the indicator, you choose an indicator that changes color during the region of the rapid pH rise. And that's going to be around where the equivalence point is. Well, let's take a look at where the equivalence point is. So the equivalence point is going to happen in the middle of the region where it's rapidly rising. For a strong acid, strong base titration, we already saw that the equivalence point was at pH 7. For the weak acid, strong base titration, first of all, the pH starts higher because we have a weak acid, so it's not completely dissociating and making as many hydronium ions as the strong acid. Then we begin to add sodium hydroxide, And since they're both 0.1 molar and we're starting with 40 milliliters of acetic acid, the equivalence point will come when we've added also 40 milliliters of sodium hydroxide. And you can see here that the equivalence point for the weak acid strong base titration happens at a higher pH than it does for the strong acid strong base titration. And this is because what's going on in this titration is that we are producing acetate ions, which themselves are a weak base. And so they cause the solution at the equivalence point to be basic. We'll go into more detail. We discussed it a little bit in the last lecture. We're going into a little more detail as we analyze the curve here. One other thing to note is the half equivalence point. And we're going to be analyzing this in lab as well. The half equivalence point is where you have neutralized half of the weak acid. So at the halfway equivalence point, which here is at 20 milliliters, here the half of the acetic acid is gone and has been turned into acetate ion. So here you have equal amounts of acetic acid and acetate ion. Let's see here. And so at this point, so if we're halfway through, looking at the Henderson-Hasselbalch equation, pH equals pKa plus log of the base over the acid. Salt over your potatoes. Now, if you're looking at the half equivalence point, at the 1/2 way equivalence point, you're going to have neutralized half of your weak acid and turned it into your conjugate base. So your concentration of your conjugate base will be the same as your concentration of your acid. And what that means is this fraction will be 1, and the log of 1 is 0. So at the halfway equivalence point, the pH is equal to the pKa of the weak acid in that titration. And so that's a little useful little shortcut there, is that if you're at the halfway equivalence point, you can actually get the pH pretty quickly. As long as the Henderson-Hasselbalch equation applies, your base and acid concentration will be the same at that point. In this case, acetic acid and acetate ion. So your pH will be equal to your pKa. Okay, so let's look at the weak acid strong base titration curve in a bit more detail here. So when we first start out, we have 0.1 molar acetic acid. And unlike when we have 0.1 molar strong acid, hydrochloric acid, the pH is not 1 because the hydrochloric acid completely dissociates. So if you have 0.1 molar of HCl, you have 0.1 molar of H+, and the negative log of 0.1 is 1, so the pH is 1. However, for acetic acid, before we've added any sodium hydroxide, there's still an equilibrium here. And we did a calculation previously of the pH of acetic acid in pure water. It's a 2.89, right? And that's what's shown right here. And so the pH is not 1 because not all of the acetic acid has dissociated. There's going to be, it'll make some H+, but it's not going to completely dissociate. There'll still be some acetic acid left over. Now we start to add, let's say we start to add sodium hydroxide, and we get to around here. So this here is called the buffer region. And it's called the buffer region because we're taking the acetic acid we started with, we add some hydroxide, and we assume 100% reaction. And again, the acid here donates the H+ over to hydroxide, and the OH- gets an H+, it becomes water. And what's left of acetic acid is it loses the H+, so you have the acetate ion. Okay. And so, like I said, when we're at the halfway equivalence point, these concentrations will be the same. And so the pH will equal the pKa. If we're anywhere along this flat part here, though, we'll be in what's known as the buffer region, because we're going to have some amount of the weak acid and some amount of its conjugate base. You'll have a fairly significant amount of both. And so because of that, when you go to calculate the pH, you can use the Henderson-Hasselbalch equation to calculate it. As long as the simplifying assumption holds and you're in this buffer region, you can use the Henderson-Hasselbalch equation to calculate the pH. So before the equivalence point, you do step 1, do 100% reaction of the strong base, and then when you go to calculate the pH, you can use the Henderson-Hasselbalch equation. When we get to the equivalence point, at this point, will have used up all of the acetic acid. So at the equivalence point, what this means is that these two, so this is the stoichiometry, these two, this is the same as this, same. And so these completely neutralize each other. So at the equivalence point, we're not going to have any of these left at the equivalence point. All that's going to be left is this. At equivalence point, only the conjugate base left. Conjugate base. Okay, so once we've gotten to the equivalence point, before the equivalence point, we've got some of the acids still left, and we're making some of the conjugate base. But at the equivalence point, the same amount of hydroxide will be added as there was acid. So both of these will be completely reacted. All that will be left is the conjugate base. So the relevant equation here at the equivalence point is the conjugate base behaving like a base. All that's left is the conjugate base and water. So that's the hard part for many students, is realizing what is the equation I have to write here. Think about what's left in the flask, in the solution. We're at the equivalence point. All the acetic acid is gone. We've added exactly as much sodium hydroxide as there was acetic acid, and we assumed 100% reaction. So they're both all gone. All that's left is the acetate ion. So we have the acetate ion and water. What's going to happen? Now the acetate ion is the conjugate base of a weak acid, so it will accept an H plus from water. So water loses the H plus, it loses an H, charge goes down by 1 unit, becomes hydroxide. The acetate ion gains the H plus, so it has the H here and the charge went up by 1 unit. And so our equilibrium is going to be the equilibrium of the conjugate base, which means that if you want to calculate the pH, you're going to need the Kb for the acetate ion. So remember here in this case, the Kb for the acetate ion, you can't look this up in a table. What you can do though is you can get it by doing the Kw over the Ka of acetic acid. And that will be the equilibrium equation you use to determine the pH. You'll find the concentration of hydroxide, and then you will get the pH. Note, you cannot use the Henderson-Hasselbalch equation at the equivalence point. Why? Because the Henderson-Hasselbalch equation only works when there's significant amounts of the acid in the conjugate base. But before you do your equilibrium here, all you've got is conjugate base. There's no weak acid left. And so it's not appropriate to use the Henderson-Hasselbalch equation at the equivalence point, because you don't have weak acid and conjugate base. You've only got the conjugate base. So do the equilibrium for the conjugate base. Fill out an ice table, Solve for X, that will be hydroxide concentration, determine the pH. That's your strategy at the equivalence point. After the equivalence point, there's no equilibrium. After the equivalence point, all that matters is how much more strong base you add. Now, is there going to be some of this weak base left, the conjugate base? Yes, but its contribution to the pH is going to be so small that that it's not going to matter. So after the equivalence point, all that matters is however much additional hydroxide you added, whatever is the concentration of that additional hydroxide, take the negative log of that to get the pOH, then find the pH. That's it. No equilibrium after the equivalence point. All of the equilibrium, the pH is going to be dominated by the excess strong base that you're adding. Another point is when we're at the equivalence point, again, all that there was the conjugate base here. For that reason, that's why the pH was greater than 7. The pH was a basic region because we had titrated away all of the weak acid and made only conjugate base, and that conjugate base behaved like a base, and of course there's going to be some increased concentration of hydroxide that results in this increased pH. But after the equivalence point, doesn't matter what weak base you've got in there, you're dumping in strong base. That's going to dominate the pH. So what we saw was a weak acid strong base titration where the weak acid had a Ka of about 2 × 10⁻⁵. So it's a titration curve like this. The weaker the acid, the higher the pH it is at the start, and so the more flat of a curve you're going to get with less rise. So it depends on how weak the acid is. That determines the shape of your curve. What about weak base, strong acid titration? Okay, so in the weak base, strong acid titration, in this example, it's a little bit different than the example you had in the lab, because in the lab, you put the ammonia in the burette and you had HCl in the flask. In this graph here, the ammonia's in the flask and HCl is being added to it. So for that reason, the pH is going down along the course of the titration because we're adding more and more HCl. So this is a weak base being titrated by a strong acid. So at the beginning of the titration, all we've got is ammonia. And so the pH of the solution is based on the base equilibrium of ammonia. And the pH will be high since it's a weak base. It's not as high as if it were a strong base, but it's fairly high. Then we begin to add HCl, okay? And again, we always assume that when we're adding the strong acid or the strong base that it reacts 100%. So here we're assuming that the strong acid reacts 100% until it's all gone. So what's going on? This is the stoichiometry part, because we're assuming 100% reaction. The strong acid giving a proton to ammonia, making the ammonium ion. And so it's got one extra H and a positive charge here, and then what's left of the hydronium is water. And so since we're in before the equivalence point, we're in the buffer region. So some of our ammonia will be converted to ammonium ion. So we'll have a significant amount of both this weak base ammonia and its conjugate acid ammonium ion. And so again, this is the buffer region. We can use the Henderson-Hasselbalch equation to determine the pH here. And also same thing. So in this case, let's say we were going to do the Henderson-Hasselbalch equation for the equilibrium. So this would be step 1, the stoich step. That's the reaction for the stoich step. Then Step 2 would be the base equilibrium of ammonia. But we can still, even though it's a base equilibrium, we can still use the Henderson-Hasselbalch equation. What we do is flip this on its head, and we get the Ka for this guy. So the Ka for NH4 plus is going to be equal to Kw over the Kb of ammonia. And then we can use the Henderson-Hasselbalch equation anyway. The pH will be equal to the pKa of ammonia plus log of the base, which is NH3. In this case, it's not the salt. This is base over the acid. So it's base over acid, though. And ammonia over acetate ion. And then if we're at the half equivalence point, then these two will be the same. And so at the half equivalence point, the pH equals the pKa of ammonium ion, which is 9.25. Now, going to the equivalence point. So this is in the buffer region. We can use the Henderson-Hasselbalch equation to find the pH. When we get to the equivalence point, at this point, all of the ammonia has reacted with all of the hydronium that was added, and all that we've got is ammonium ion and water. At the equivalence point, all this is gone, all this is used up. At the equivalence point, all we've got are these. So the relevant equilibrium reaction is ammonium ion and water reacting. And so here we get the ammonium ion giving the proton to water. It makes hydronium and ammonia. To determine the pH at the equivalence point, it's going to be dictated by the Ka for the ammonium ion. So the K for this reaction here, the K for this reaction equals the Ka of ammonium ion. And so we would use that equilibrium. We would set up an ice table, and do an equilibrium calculation. We cannot use the Henderson-Hasselbalch equation at the equivalence point because there is not a significant amount of ammonia. It was all used up when we did the titration. At the equivalence point, mostly we've got ammonium ion and water. So we have to do an ice table and do an equilibrium calculation based on the amount of ammonium ion. And again, the Ka for the ammonium ion can be determined from the Kb for ammonia. So ammonium ion is a weak acid. It's the conjugate acid of this weak base ammonium. So it itself is an acid. So if all we've got in the solution now is ammonium ion and water, the solution is going to be acidic. And that's why the pH at the equivalence point is less than 7. It's because the ammonium ion, which is what we have in there now at the equivalence point, is acidic. And so it gives away protons and causes the solution to be acidic by this equilibrium right here. In terms of the indicators, as you guys saw in your titration, phenolphthalein was not a good indicator for this titration because it does not change color in the region of the curve that changes quickly in pH. A good acid-base indicator is one that changes color at a pH near to the equivalence point. Like methyl red is a great indicator for this titration because it changes color right in the range of the equivalence point. Of course, an indicator that changes color here might work, or here, because it will change color in the rapid pH change. But the best indicator will be the one that changes color at a pH that is close to the equivalence point. Finally, once you pass the equivalence point, what matters there is just the extra strong acid you're dumping in. In this titration, we've already neutralized all the ammonia. So now we're just adding additional H+, additional H+. Yes, we have the weak acid ammonium ion. We've got some ammonium ion. Yes, ammonium ion's in there. But it's nothing compared to straight up adding H+, because it's going to have an equilibrium. But here we're adding strong acid. We're just dumping in H+. So past the equivalence point, you don't have to worry about equilibrium. You just determine the concentration of any extra added HCl or H3O plus past the equivalence point, and take the negative log of that concentration, and that will get you the pH. So past the equivalence point, equilibrium doesn't matter anymore. It's about how much additional strong acid that you added. So for review, what I've shown you for each of these three types of titrations, strong acid, strong base, weak acid, strong base, strong acid, weak base, particularly for the weak acid, strong base, and strong acid, weak base, there are two steps you have to do. Number one, consider the stoichiometry and assume the complete reaction of the strong acid or strong base. If you are before the equivalence point, you will be in the buffer region, and you'll have significant amounts of weak acid conjugate base, weak base conjugate acid, so you can use the Henderson-Hasselbalch equation to determine the pH. At the equivalence point, all of your initial amount of weak acid or base will be consumed. Your pH will be decided by an equilibrium calculation based on the conjugate acid or base that remains. After the equivalence point, doesn't matter what the acid or base was. There's no longer any equilibrium to speak of. All that matters is what is the concentration of the excess strong acid or strong base that you added. You don't need to do an equilibrium calculation. You simply determine that concentration of hydronium or hydroxide and calculate the pH from that. No equilibrium. The last type of titration I'll talk about, one that we're going to do a lab about, experiment 12. That is a titration of a polyprotic acid. And so here is a titration of a polyprotic acid, a diprotic acid, in fact. So here we see that it is starting at a low pH, so that's how we know it's an acid. We're adding sodium hydroxide. The pH is slowly rising until we get a first steep rise in the pH. This is the first equivalence point. So here, the first steep rise here is the loss of the first proton from the diprotic acid. So we have a diprotic acid with 2 protons. It's losing its first proton, and so now all that's left is the one without a proton. So what's going on is we're starting with an acid that's been called H2A plus. It doesn't have to be positive, it could be neutral, but we're adding hydroxide until we remove 1 proton from the acid. Then that's the first equivalence point. Then we're going to add more hydroxide until we lose the second proton. This is the loss of the second proton here. And just as we saw before, in the buffer regions, the pH is equal to the pKa. But for diprotic acids, they have 2 Kas. They have the first Ka with the loss of the first proton, and the second Ka with the loss of the second proton. When it comes to the diprotic acid, just like the monoprotic acid, at the halfway equivalence point, the pH equals the pKa. But halfway to the first equivalence point, the pH will equal pKa1. And you're going to use that property in your lab to determine the pKa1 of a diprotic acid. You're going to find out what is the pH at the halfway equivalence point, and the pH there will be the pKa1. Then you'll watch the titration, you'll watch a steep rise for the loss of the first proton. Then you'll get to a second buffer region, halfway to the second equivalence point. Here, halfway between the first and second equivalence point, the pH will be equal to the pKa2 of the diprotic acid. And so you'll use that to figure out the pKa2 for a diprotic acid. And then you'll pick the relevant diprotic acid from a list of known diprotic acids based on their known pKa's. And so that's it. That's all you really need to know about the titration curve of diprotic acids. You're going to be doing a lab on it. You're not going to do any calculations here. The calculations for this are exceedingly complicated. I know I did them one time a long time ago, but you don't have to do those. All you'll have to do is find the halfway to the first equivalence point. pH there will be equal to pKa1 for the diprotic acid. Then you'll find the pH halfway between the first equivalence point and the second equivalence point. pH there will be equal to the pKa2. And so that concludes my lecture about the strategy behind how to set up a calculation for a acid-base titration and how to analyze a titration curve for an acid-base titration. This is really important because a lot of times people start calculating and they haven't even really figured out what it is that they're calculating. The hardest part for these problems is deciding what reaction is relevant right now. What K am I going to use to do my equilibrium calculation? What K for what reaction? What reaction is going on here? So hopefully this description has given you an introduction to how you think about that. In the next lecture, we're going to apply that to calculating the pH of a titration at various points along the titration. And that will be the next entire lecture and it will be for a weak acid, strong base titration. Then next week, I'll go through an entire problem where we'll do a strong acid, weak base titration. But this week, we'll focus on strategy, and also we'll focus on the buffers and weak acid, strong base titration. As I said, it's a big topic, and so make sure that you understand what it is you're doing. Read the textbook. Homework is limited. I don't want to bash you over the head with homework, but these do take a lot of practice if you want to be able to get them right and really understand what it is you're calculating. So I have advised additional problems from the homework, from the textbook beyond the homework, and I very, very strongly suggest those for you over the course of the next week, this week and next week. So yeah, next lecture, going through and calculating along the titration curve pH for a weak acid strong base titration. See you then.